Right, so hello again. So let me just check if everybody is already here. So just give me a thumbs up. Okay, great. So most of you are already here. Okay, so any questions so far regarding with the example number 2? All right, so it seems that there is no question. Okay, let's now proceed to the third example. So the same unknowns to solve for the voltage output on this label VO, the total current of the circuit, the total resistance of the circuit, and then the power across R1. Okay, this one right here. So here is the, oops, before that one. Okay, so what is the value of our VO, or where our VS will flow? Okay, so is it on germanium or is it on silicon? Or is it both? Hello, hello. Anyone who would like to guess? So where we're okay.
It should be both, but I think they will oppose lesser. It will be both in a parallel way. I don't know because they are parallel to each other.
Yeah, you're actually correct also with that one. But let's go back with the basics of electricity. So again, if our electricity only has a choice, it will always go to the path that has a lesser resistance, and then that has a lesser voltage drop. Okay, so in here it will actually only flow on one side. Okay, why is that? Because the other one will become an open switch. So how will that happen? Okay, so in here we have this flow of current, or flow of voltage. Okay, and let's assume that it will only flow on one direction. Okay, well, of course it will only flow on a lesser voltage drop, and then a lesser resistance. So in other words, it will flow on the germanium. Okay, and as a result, if it's now flowing on the germanium, we now have this kind of current. So some of them will go here, and then some of them will go here. And then as a result, we now have a positive to negative connection on the silicon diode, and then negative to positive connection on the silicon diode. So if it's in reverse bias, so this will become an open switch already. Okay. And if you guys are going to take a look on this one, we have a reading of 6.7 volts, because that's 7 minus 0.3. We have 6.7 volts for the germanium. But if you're going to do that one the other way around, wherein, let's say, we've chose the silicon diode, it will flow right here. Oops. Wherein we have a flow of current right here, and this side, and then we have this flow of current. So this will become an open switch since it has no connection of reverse bias. But in here, 7 minus 0.7, we now only have a remaining 6.3 volts. And of course, we don't want that to happen, or in terms of electricity, he doesn't want that to happen. Okay, because again, the electricity will always flow on the lesser resistance or lesser voltage. So if we are going to choose which one is better, oops, 6.7 volts or 6.3 volts. So of course, it will be the 6.7 volts. So this is the correct assumption, okay, and this is the incorrect assumption flow of current. Okay, so in other words, when it comes to diode, it only when it comes to a parallel connection of diode, okay, it will only flow in one diode. Okay, so even though you have other diodes right here, and then another diodes right here, so it will only choose whichever is the smallest voltage drop, okay, and then the smallest resistance. Okay, so that is the rule when it comes to diodes. So that is why in here, this is the correct flow of current. Okay, and then going here. And then this will become an open circuit. So you can just simply remove that one. All right. So here is the answer for the solution of number 3. We have 6.7 volts. And then for the I total, we have 6.7 divided by 5K, which is the total resistance. And then you will get 1.34 milliamps. And then R total is 5K ohms. And then the power across R1. So just use this formula. So P is equal to IR1 times VR1, which will give you the this one. So for the VR1, we have 1.34 milliamps times 5K. And then the IR1 is 1.34 milliamps. And as a result, it will give you an answer of 8.978 milliwatts. Okay, so before we go on this another situation, okay, or scenario, let's clear the solution on number 3 first. So again, just give me a thumbs up if everything is clear.
Excuse me, sir. I want to ask, in case we have two diodes in parallel connections like this, do we consider the one with lesser threshold value first, or do we consider the bulk resistance in case they have bulk resistance that are not negligible? Which one do you consider first? Is it the
You should consider
threshold voltage first,
you should
or the
consider
bulk
everything
resistance first?
all. Okay. So all you need to do is compute whichever has the higher voltage output, okay, at this point. And then
Okay,
whichever is the highest, then that is the one that you need to consider. Okay.
okay. Thank
But
you.
most likely, you know, just comes with the voltage threshold because it's so unrealistic if we have a 100 ohms or 1 key ohms on a certain diode. So again, mostly it's just less than 1 ohm, or if it's more than 1 ohm, then it should be 1 point something only. Okay, so there is no way that it will reach 2 ohms. Okay,
Sir,
yes.
sir, what if they are both germanium?
So if they are both germanium, then you have to consider both. Okay, so we now have a split of current. So flow of current on the upper and then flow of current on below. Okay.
Okay, sir. Thank you, sir.
Okay, so we actually have an example like that later on, I guess. So any other concerns? Okay, so it seems that there are no questions anymore. So let's go back on this scenario or circuit. So this is the effect of a short circuit. Okay, so again, reminding you guys that the flow of current, uh, you know, works like this. So initially we have this, this circuit wherein we have the R1, okay, which has a resistance of 2 key ohm, but then we shorted this one, okay. So we put a jump wire on this one. So when R1 is shorted, its resistance is voided and subtracted to the total resistance value. It is simple terms bypass. So in other words, even though we have a split of current in here, but then again the electricity will always go at the lesser resistance or lesser voltage drop, or the one that it will always have a higher voltage output. So as a result, it will blow on this metal wire. Okay. So remember that current travels the path of least resistance. So this is why when the metal wire was placed before and across R1, the current travels through the metal wire instead of going through R1. So even though R1 is still connected to the circuit, it has 2000 ohms more resistance than the metal wire, and this makes it least desirable for the current. Okay, so I hope this one cleared up your what is one? Mm, what is a proper term? Uh, yung pagdududa. Okay. Doubtness. How do you call that one in English? For confusion. Okay. So I hope this one will clear that confusion of yours. Or yung hindi pagdududa yung tamang term sa Tagalog. So sorry for that one, Mr. Segun, but I cannot find the term of the word pagdududa for now. But yeah.
It's alright.
Mhm. Okay. So again, we're done with the solution of number 3. And then here's now another example for the number 4. So the same unknowns. So we have the VO, okay, the total current, total resistance, and the power across T1. Okay, so first question. Okay, so what is the value of our V sub 1? Oops, I think it's not that easy. You know, I think you guys have to use your calculator, and then at the same time, you have to solve the total current first. Well, anyway, so in other words, we have to deduct the R1 first, the voltage drop across R1, and then we have to deduct the 0.7, and then whatever is the result, that is your voltage on this VO right here. Okay, so here is the solution. So using Ohm's law, we have Vs, okay, minus VR1, and then minus VB1, okay, and then we have the Vs, and then the value of your current, okay, which is 1.33 milliamps. So for you to be able to get the current, so we have this one right here, so 9.3 divided by 3k plus 4k. So 9.3 is the total voltage, okay, that is flowing on the entire circuit. So 10 minus 0.7 is 9.3. And then we have two resistance, which is in series with each other. So just add them. So 3k plus 4k. So just use your calculator and you will get 1.33 milliamps. And then after getting this current, then you can now use that one to get the voltage across R1 or the voltage drop across R1. So 1.33 milliamps times 3k, okay, because that is the resistance value of the R1 minus the 0.7 volts. So as a result, we have here 5.31 volts on our VO. So just use your calculator to check the value of VO and then the value of I. So you can also apply KVL, okay, Kirchhoff's law. So just have a loop in here. So we can use clockwise or counterclockwise. So that depends on you. But in my case, I always use the clockwise. Call this one clockwise. I forget the term, but it's a clockwise way. Okay, something like that. Okay. So in here, you will be able to get the this kind of expression. So 10 minus 3k times I minus 0.7 minus 4k times I. And then just simplify everything. And then you will get this final equation, which is 9.3 divided by 7k. And then you will get the same result, which is 1.33 milliamps for the total current. And then for the R total, so of course it's 3k plus 4k, so we have 7k ohms. And then for the power across the diode, so just get the current, okay, or the total current, which is 1.33 milliamps, multiplied to the voltage threshold, which is 0.7, and then you will get 0.0931 milliwatts. Okay, so again, just let me know if everything is already okay and you were already able to verify everything. Okay, so there were two. What about the others? Okay, great. So it's like half of you were already able to get this one. Anyway, so you can always go back on the slide just in case you want to verify something or you want to check something. So let's now proceed to the example number 5. So we have a parallel connection now. So solve for VO, total current, the current on each diode, and the total resistance. Okay, so question, what is the value of our VO? So it will be 8 minus the voltage drop across R1. I just remembered. No, it's not like that. Okay, because since they are now in a parallel connection and we don't have a bulk resistance, so any guess? Anyone? What is your answer in VO? Okay, so it seems that most of you doesn't know how to start or doesn't know how to, uh, cut this one, uh, calculate maybe what is the value of our VO. But to make it simple, if we have this kind of circuit, especially the parallel connection of the diode, okay, so it is always this one, okay, whatever is the threshold voltage, okay, that is near to your VO, okay, that is the voltage output, okay, which is actually 0.7 volts. So how did it happen? So remember that if it's in a forward bias, so remember that if it's in a forward bias, so this one works like an open, ah, sorry, it works like a closed switch. Okay, so in other words, you can just simply remove that one and then replace those two a wire. Okay, and the only remaining component in here is like a voltage source, which has a polarity of negative and then positive. So we have 0.7 volts in here. So the same, it is one negative and then positive, which is 0.7 volts. Okay, so all of our voltage and then currents will pass through this 0.7 and then 0.7. Okay, and then we'll go back right here. So it will never flow on this path because of course it has to go back to its loop. So the only remaining voltage that is flowing on this circuit right here is this 0.7 volts. Okay, so that is why we have 0.7 volts as our VO. Okay, and then for the total current, so we'll just get the total current, I mean the total voltage and then the total resistance. So we have 7.3 divided by 3K. So you can do this one for now, wherein we've only deducted one silicon diode. Okay, but when it comes to solving for the individuality of those diodes, just divide it by 2, since we have the same diodes anyway. Okay, so 2.43 milliamps divided by 2 is equal to 1.215 milliamp on each diode. However, if this one is, let's say, germanium, so let's just say that this is germanium. So this will be neglected already, since it will always flow on one diode only, okay, which is the lesser voltage drop. So instead of 0.7, this is now 0.3 volts. And then our VO now is, of course, 0.3 volts. Okay, but since we have the same, okay, diode, then our current will flow on both diodes. Okay, so for the individual current, just get one first, and then you can divide it by 2, and then you now have the individual current of your diodes, which is 1.215 milliamp on each diode. And then for the R total, we have 3 kiloohms. So are we clear so far? What about the others? Okay, so let me call those people who are not responding. Mr. Santa Cruz.
Yes, sir.
Okay, Mr. Mina. Mr. Mina, are you around? What about you, Mr. Fabian? Mr. Fabian?
Yes, sir.
So,
I
any
thought
questions?
it. Nothing, sir.
Okay, wait. So, baka nakatulog ka na dyan, ha?
Hindi, sir. Fugyan kasi yung pagkarinig ko, sir.
Ah, okay. All right, so yeah, that's it for the, example number 5. So let's now move on to the example number 6. So solve for VO, total current, and then the total resistance. So in here, you can have two approach. Okay, since you have two separate voltage source, so you can have this one or you can have this one. Okay, so it will give you the same result. So you can use this upper expression or this lower expression. Okay, so V1 minus the 0.3 and then minus voltage drop across R1, and then that is now your answer for the VO. So the same as one. So V2 minus the voltage drop across R2 and then 0.7, and then that will be now your answer for the VO. So here is the solution. So using Ohm's law, you have this upper expression. So V1 minus VD1 minus VR1, which will give you 6.56. And then for the lower expression, which is this one, so this will give you V2 plus VR2 plus VD2, which will give you 6.55. So they might just differ when it comes to decimals, but they are super close to 6.56 and then 6.55. Okay, but of course, for you to be able to get this answer, you have to get the current first, or the total current. So you can use Ohm's law. So V total divided by R total. So this is the V total. So we've just considered everything. So 12 minus 0.3 minus 0.7. Okay, and then minus 0.7 and then minus 7. Okay, and then for the R total, we have 2K plus 5K. And then we have a result of 2.57 milliamps. So you can also apply KVL, okay, in order for you to be able to get the current, which will give us the same result, of course, which is 2.57 milliamps. And then for the R total, so it's 2K plus 5K, since they are in series connection. So by the way, this one is connected, okay, in our V1. So V1 and V2 is connected with each other. So again, I'll give you guys 20 seconds to 40 seconds to analyze everything. And if you have a question, so just let me know. All right, so what about the others? So there were already maybe 5 who were able to get this one. Okay, great. So let's now move on to the last example, which is the example number 7. So solve for VO, total current, and then the total resistance. All right. So without looking on the solution, so what is the value of our VO? Anyone who would like to guess? Okay, so let me call someone. Mini, mini, mini mo. Okay, Mr. Carlito Gangas.
Sir, di pa ma-solve, sir eh. Try pa po.
Okay. All right. So let me teach you guys, the quickest way to solve if we have this like, quite complex circuit. So if you have a This one is quite unclear, but this one is in a series connection. Okay, so this one is connected on this V2. So you can do this one, like you can solve for the upper, okay, to solve for the VO, and the same with the V2 since they have the same flow of current. So if you have the same flow of current and then you have two, different voltage source, then you can do that one, okay. But if you only have one voltage source, then you just have to, use the one that has a voltage source. So it could be on the above or on the lower. But in here, this one is not a series connection anymore. Okay, so we could see that V1, V2 is in series, but V3 is not. Okay, so let's just assume that V1 is a separate connection and V2 is a separate connection, and then V3 is a separate connection. So again, the rule of our, in electricity, so whichever has the highest voltage source, okay, that is the one that will dominate the entire flow of circuit of your current. Okay, so if you guys are going to take a look on this one, A, 12, and then 3. So basically, of course, V2 is the one that will dominate the flow of our current. So we have the flow of current that is going from here to there, and then from here to there. Okay, so let me just write this one. So we'll be having a flow of current from here to there, from here to there, and then at this point, it will split into two again. Okay, so in other words, the only one that will flow on our VO is this V2. So for you to be able to get the VO, so just deduct the voltage drop on the silicon. So 12 minus 0.7 will give us a result of 11.3. Okay, or again, you can, try to calculate everything. Okay, like you want to maybe test this one, so this will give you 8 minus 0.7. So as a result, this will give you a value of 7.3 volts. So for this one, we have 3 volts minus this voltage drop right here. So you will have a lower voltage that will flow on the VO. So of course, the highest will be the one who's going to win. So we have 11.3. So this is most likely the correct assumption rather than the 2, okay, for the V1 and then V3. So in here, we have 11.3 volts, and then for the total current, so just get everything. So we have V2 minus VB2 minus V3, okay, divided by the resistance, and then you will get, where is it, 2.86 milliamp. Okay, and then for the R total, we have 5 kiloohms. So are we clear so far regarding with this example?
Excuse me, sir. So in calculating our I total, we will not consider V1, right?
Oh yes, we will not consider V1 since
Okay, thank you.
it will dominated by the V2. So, and then this will become an open circuit. And this will be considered since it doesn't have a diode. Yeah. So it will be part of this circuit right here.
Okay, sir.
All right, so that's actually it already for the module 2. So, this is summary. We've just talked this ideal diode, which is the first approximation, second approximation, and then third approximation. So we have more complex examples. So the examples that I have it here are just the basics for you guys to understand it real quick, and then the fundamentals. So I would like you guys to search more on the internet, or you can visit the practice exercises that I have put in here. So this is just to recall, what is diode approximation, and then analog electronic circuits questions and answer about diode approximations and series connection. And we also have a website from ProProps, and yeah, two ProProps. Okay, so just check them out. Okay. So they talk about diodes and then the approximations. Okay, so again, don't forget that you guys are going to have a quiz. So quiz and approximation, and then quiz on diode circuit problem in series and parallel circuit, and then the case study. Okay, so if you guys don't have a question or clarification anymore, then you guys may now go, and thank you guys for coming. I really appreciate it, and keep safe. Okay?
Sir, thank you, sir.
Thank you,
Thank
sir.
you.
Thank you
Thank
too.
you, sir.
Thank you, sir.
Thank you too. Yes, Mr. Alan and Miss Maxine. Anyway, goodbye guys, and thank you again.